Hello everyone, welcome back to the LMS initiative of the Department of Collegiate and Technical Education. So all of you know that we've been discussing about the course Mass Transfer 1. So this is a course that is being taught under the Diploma in Chemical Engineering program for the students of the SJ Government Polytechnic. So we already have completed the fourth session of the first unit Principles of Mass Transfer. So now we are into the fifth class of the first unit. So, as usual, let us go back quickly to recollect what we studied in the previous session. So, in the last session, we took up the molecular diffusion case in gases. So, under this, we derived the flux equations for case of steady state diffusion of A to non diffusing B, and also we derived the different kinds of flux equations in terms of different types of concentration terms under equimolar counter diffusion within the gas phase. So let us in the same way derive the equations for molecular diffusion in liquids. So accordingly, these are the contents for today's session. So one is we are taking up the molecular diffusion in liquids. So then we are deriving the flux equation for steady state diffusion of A to non-diffusing B, and later on we'll derive the equation for steady state equimolar counter diffusion. So when we discuss the steady state diffusion of A through non-diffusing B under that is for gases, so I gave you one example for that case, that is gas absorption, which involves the absorption of ammonia in water from air. So there the two phases are involved. One is a gas phase containing ammonia and air. The other one is a liquid phase containing liquid water. So if ammonia has to get transferred from gas phase to liquid phase, then first it has to diffuse through the gas phase. That is, it has to diffuse through those of air, and then when it comes to interface, it gets diffused from the interface to the liquid phase, that is into the water. So in the same way, the water becomes the non-diffusing component because it is not undergoing transfer from phase to phase. So only ammonia is diffusing. So this is a typical example for steady state diffusion of A to non-diffusing B in case of liquids. So here ammonia is a component A because it is undergoing diffusion, and water becomes the component B which is not undergoing any kind of diffusion. So for the present case, we know that under steady state conditions, the flux of component A, Na, will be constant, and since water is not diffusing, that is component B is not diffusing, then NB will be equal to 0. So let us now substitute this in the basic equation that is relating the two kinds of fluxes. So Na equals Ja plus Xa into Na plus Nb. So when we wrote this equation for gases, I used the term Ya for mole fraction. So because for gases we use usually the Ya to represent the mole fraction, and when we consider liquids, the concentration, that is the mole fraction concentration terms, are usually represented using the letter X. So the equation becomes Na equals Ja into Xa into Na plus Nb. So let us now expand this equation using the fixed law of diffusion statement. So before that, let us simplify the equation by cancelling that Nb, because Nb is equal to 0. The equation gets reduced to the form Na equals Ja plus Xa Na. So now shift all the Na terms to the left hand side. So take out the Na outside as a common term. So then in the bracket what you get is 1 minus Xa on the left hand side, and whatever that is left on the right hand side is a Ja. So now let us write down minus dAb dCa by dZ for Ja on the right hand side. the equation becomes Na into 1 minus Xa is equal to minus DAB dCA by dZ, which can be written as minus DAB C into dXA by dZ. So that is because Ca will be equal to C into Xa. So since the total concentration C is constant, so you can take it outside along with DAB, and whatever that remains within the differential sign is Xa. Now we can simply separate the variables in the given equation and integrate between the limits. So take that dz term to the left hand side. So the equation becomes Na dz is equal to minus dabc into dxa by 1 minus xa. Integration of this equation between the limits z1 to z2 on LHS and xa1 to xa2 on right hand side. So if the diffusion of A is occurring between two locations z1 and z2, so initial point is z1 where the concentration of A can be taken as xa1, and the final point, that is a location where the diffusion is ending, so that is at that point the mole fraction of A is xa2. So we can integrate the equation between these two limits. So on the left hand side, the integration of z dz becomes z2 minus z1, which can be uh, simply written as z, the distance over which diffusion occurs. Then on the right hand side, take that negative sign into the integration term. So then dAB into C. So the integration of dxa by 1 minus xa will be ln 1 minus x. So if you substitute the limits and consider that negative sign also, in the numerator it is 1 minus xa2 divided by, in the denominator, 1 minus xa1. Here, what we can do one more change to the equation. The average molar concentration of the given solution, that is C, can be written in terms of the average ratio of density to molecular weight of the solution. So this is how we can express the total concentration in case of liquids. So C or C average is the total average concentration of the solution between the location 1 and 2, which is nothing but can be written in terms of rho by m average, which is equal to the rho 1 by m1 plus rho 2 by m2 whole divided by 2. Here in this one, rho 1 and rho 2 are the average densities of the solution at location 1 and 2. In the same way, m1 and m2 are the average molecular weight of the solution at z1 and z2 respectively. So then the equation becomes Na equals dAB by z into rho by m average. So that is a term replacing C in the previous equation, ln 1 minus xa2 by 1 minus xa1. So now, just like we did in the case of molecular diffusion in gases, so 1 minus the mole fraction term will be equal to the mole fraction of other component, since this is a binary mixture. So 1 minus xa2 on the right hand side is equal to xb2. In the same way, 1 minus xa1 in the denominator is equal to xb1. So now if you subtract 1 minus xa2 and 1 minus xa1, then you will get xa1 minus xa2 on one side and xb2 minus xb1 on the other side of the equation. So what we can do is we can multiply and divide the right hand side of the equation by xa1 minus xa2 in the numerator and xb2 minus xb1 in the denominator. So that kind of change to the equation we are doing in order to get the final equation in terms of the concentration difference involving xa1 and xa2, because the component A is the one which is undergoing diffusion, so the concentration difference should come in the right hand side along with the coefficient. Okay, so after doing that thing, then whatever that is there in the denominator, xp2 minus xp1, and that ln xp2 by xp1, if it is taken to denominator, it becomes xp2 minus xp1 divided by ln xp2 by xp1, which can be written as xbm. So then the equation becomes Na is equal to dab divided by z xbm into rho by m average into xa1 minus xa2. So now this whole term dab by z xbm into rho by m average together are a group of constants. So that whole thing represents the coefficient. Then on the left hand side Na is the rate of diffusion, and the other term on the right hand side xa1 minus xa2 is the concentration difference or the concentration gradient. Now your rate equation is of the form rate equals coefficient into concentration difference. So this equation can be used to calculate the flux of Na for the steady state diffusion of A to non-diffusing B in case of liquids. So the above equation, in the same way as we did in diffusion within the gas phase, can be written in terms of other types of concentrations. So Na is equal to dAB by Z xBm into rho by m average into XA1 minus XA2 can be written as CA1 by C minus CA2 by C. Now that C being a common in both the terms inside the bracket can be taken outside the bracket. So that C and the rho by m average in the numerator. So both gets cancelled. So because rho by m average is nothing but the average molar concentration, which is again equal to C. So that into C gets cancelled and the equation gets simplified to the form Na equals dAB by Z xBm into Ca1 minus Ca2. Now this equation is again of the form rate equals coefficient into concentration difference. So that dAB is a diffusivity of A into B, and Z, that is a diffusion distance, xBm, that is a log mean mole fraction of component B, all together represent a group of constants giving you the coefficient for the given equation of flux. Now let us take up the other case of diffusion under liquids, that is steady state equimolar counter diffusion. So this is again the kind of diffusion that occurs in operation like distillation. So we all know that distillation is that operation where the two components diffuse at the same time in opposite direction. Means there is a transfer from the liquid to vapor, and at the same time there is a transfer from vapor to liquid as well. So if more volatile component is diffusing from liquid to vapor, then the less volatile component will be diffusing from the vapor to liquid. So when this diffusion is occurring under steady state conditions, then if you consider just the liquid phase, then the more volatile component and both less volatile component will be diffusing in opposite directions. So let us derive the equation for flux for this condition. So in this case, both Na and Nb will have values, but if Na is positive, then Nb is to be taken as negative. That is because the diffusion is occurring in opposite directions. So let us now write down or substitute these two Na and Nb terms in the given basic equation of flux of A. So Na is equal to Ja plus Xa into Na plus Nb. So here Na plus Nb gets cancelled because Na is equal to minus Nb. So then the whole term, that is the second term in the right hand side, gets cancelled. It becomes 0. So what you are now left with is just Na equals Ja. So on Na on the left hand side will be equal to Ja on the right hand side. So let us expand the Ja term from fixed law statement. So Na is equal to minus dAB dCA by dZ can be written as C dXA by dZ. Now, so we can easily separate the variables in this equation and integrate between the limits. So shift the dz term to the left hand side. becomes NAdZ is equal to minus DAB C dxa. Integrating this equation between the limits z1 to z2 on the left hand side and xa1 to xa2 on the right hand side. So then we'll get the equation as Na into z2 minus z1 or Naz on the left hand side. On the right hand side it is minus dab. So C can be written in the same way as in the previous case as rho by m average. Then inside the bracket it's xa1 minus xa2. So now we have got the equation in a much simpler way in this particular case. So we don't have to do any changes to the equation because already we have the xa1 minus xa2 in the equation on the right hand side. So shift the z term to the right hand side. The final equation is Na equals dab by z into rho by m average xa1 minus xa2. So in this equation, the dab by z into rho by m average, the whole term is a coefficient. So on the left hand side you have the rate, then on the right hand side it's the product of coefficient and the concentration difference expressed in terms of mole fractions. So the same equation can be changed to represent the equation in terms of Ca1 and Ca2 instead of Xa1 and Xa2 as follows. So Na as it is on left hand side equals dab by z, then rho by m average. So inside the bracket, instead of Xa1, we can write it down as Ca1 by C because the mole fraction of any component will be equal to the ratio of the molar concentration of that component to the total molar concentration. So then Xa2 can also be written as Ca2 by C. So C being common in both the terms can be taken outside the bracket and this C gets cancelled with the rho by m average because rho by m average is nothing but the total average concentration of the given solution. Okay, then the equation becomes Na is equal to dab by z into Ca1 minus Ca2. So this is again the another final form of the equation. It is of the form now the flux is equal to coefficient into concentration difference. The coefficient in this case is dab divided by z. The concentration difference is in the term in the form of Ca1 minus Ca2. So as I said in the beginning itself, the total concentration can be written as C or C average, which is equal to or which can be expressed as the average ratio of density to molecular weight of the solution at location 1 and 2. So C average or rho by M average is equal to rho 1 by M1 plus rho 2 by M2 whole divided by 2. So that C average is the total average concentration of solution containing A and B in kilomoles per meter cube. So rho 1 and rho 2 are the average densities of the solution in kg per meter cube at location 1 and 2 respectively. In the same way, the capital M1 and M2 are the average molecular weights of the solution at location 1 and 2 respectively. Now let us use the equations derived to solve a typical problem where the steady state diffusion occurs in case of liquids. So let us read the question first. Hydrochloric acid in bracket A means HCl represents the component A at 283 Kelvin diffused through a thin film of water. Okay, a film of water is there. So that film through which the HCl diffuses, the film is 4 millimeters thick. Means this is the distance over which the diffusion is occurring. This HCl is undergoing diffusion over a distance of 4 millimeters of water. The concentration of A at location 1 on one boundary of the film is 12.8% So here the concentration is given in terms of weight percent, and in bracket for the purpose of conversion to mole percent, they have given the density. So the density at that boundary, that is at the starting location of the diffusion, that is rho 1 is equal to 1060.7 kg per meter cube, and at location 2 on the other boundary of the water molecule, uh, the concentration of HCl is 4 weight percent. So the diffusion is occurring from location 1, that is on the one boundary where the concentration is high of 12 weight percent. So it is occurring up to the other location, that is other boundary of the water film where the concentration is lower, that is 4 weight percent. So also the density of the solution at location 2 is also given. So it is rho to 1020.15 kg per meter cube. So the diffusivity of HCl in water, DAB, is also given. It is 2.5 to 10 to the power of minus 9 meter square per second. Then using all this, you have to calculate the flux of diffusion of A, assuming water to be stagnant, that is non-diffusing. Since the other component involved, that is water, is a stagnant, means it's not moving, means it is a non-diffusing component. So we can apply the flux equations that have been derived for steady state diffusion of A through non-diffusing B in case of liquids. Okay. So here to calculate the average molar concentration, so we require the molecular weight of the two components. So let us first calculate the molecular weights of one component, that is HCl. Molecular weight is 36.5. So and the molecular weight of water, we know that it's 18. So then the average molecular weight of the mixture at location 1, that is on one side of the water film, that is on the first boundary, or directly we can calculate the mole fraction of the component A, that is HCl, at location 1. So XA1 is equal to, we have the weight percent, so that weight percent divided by molecular weight of that component will give you the mole percent. Okay. So in the same way, in the denominator, so 12 represents the weight of HCl per, if you're starting with a 100 kg solution. So 12 divided by the molecular weight of HCl, that is 6.5, plus the remaining amount, 100 minus 12 of HCl represents that of water, divided by 18. So this calculations gives you the mole fraction of HCl at location 1. So it is of the value 0.063. So from XA1, first let us calculate XB1. So XB1 is equal to 1 minus XA1, 1 minus 0.063, it will be equal to 0.937. Similarly, now let us calculate the average molecular weight at location 1. So M1 is equal to 100 is the total weight of the mixture that we have considered, divided by the weight of HCl is obtained by dividing 12 by molecular weight of HCl. So 12 divided by 36.5 plus 100 minus 12 divided by 18 gives you the total moles of the mixture. So 100 divided by total moles gives you the molecular weight at the location 1. So it is of about 19.166 kg per kilomoles. So now similarly, in the same way, we can do the calculations for location 2. So XA2 will be equal to, where it's given that the concentration of HCl at the other boundary is 4 weight%. So accordingly, XA2 will be equal to 4 divided by 36.5 in the numerator, and in the denominator 4 divided by 36.5 plus 100 minus 4 divided by 18. So the first term under the denominator gives you the moles of HCl, and the second term will give you the moles of water. So when you add these two, will give you the total moles of the given mixture at location 2. So the moles of component A divided by the total moles of the mixture is giving you the mole fraction of that component XA2. So it is of the value 0.021. So now from this we can calculate XB2. XB2 is nothing but 1 minus XA2. So 1 minus 0.021 is equal to 0.9799. So let us now calculate the average molecular weight at location 2. So at location 2 also we have 100 kgs of the solution divided by the moles of component A is the weight% of component A, weigh 4 divided by the molecular weight, that is 6.5. So plus the moles of water is obtained by subtracting the moles of A from, that is a weight% of A from 100. So it is 100 minus 4 divided by 18. So this calculation gives you the average molecular weight of the mixture at location 2. So then M2 will be equal to 18.3728 kg per kilomoles. Now the average concentration of the mixture C average or rho by M average will be equal to, so rho 1 by M1 plus rho 2 by M2 whole divided by 2. So rho 1, rho 2 are given in the question. Substitute the values and get the average concentration as 55.4336 kilomoles per meter cube. So now for the purpose of substitution, let us calculate the value XBM. So we know XB2 minus XB1 divided by ln XB2 by XB1 will give you XBM. So substitute the values of XB2 and XB1 in the given equation. It gives you a value of 0.958, which is the log mean mole fraction of component B, that is XBM. So also the distance over which the diffusion takes place is given. So as it is given that the water of thickness, the water film of thickness 4 millimeter is the distance over which the HCl is diffusing. So Z is equal to 4 mm. So in SI unit it becomes 0.04 meters. The flux equation for the diffusion of A through non-diffusing B in terms of mole fractions is like this: Na equals dAb by Z xbm into rho by m average into xa1 minus xa2. So dAb is given 2.9 into 10 raised to minus 9 into rho by m average is 55.4336 into xa1 is 0.063, xa2 is minus 0.0201. In the denominator, it is x into xbm, z into xbm. So z is 0.04, xbm is 0.958. So after you do the calculations, the Na value what you get is 1.55 into 10 raised to minus 6 kilomoles per meter square second. So this is the answer for the given problem. So that is how we can use the flux equations for various cases of diffusion to calculate or to estimate the rate at which the diffusing component is undergoing transfer from higher location end to the lower location end. So that's all for today's class. So in this class, we learned how to derive the rate equations in case of molecular diffusion within the liquid phases, and also we solved a problem using the derived equations. So with that, let us conclude the fifth session of mass transfer. Thank you for listening. Let us again meet in the next session, that is session number 6. Thank you.